Greetings, ladies and gentlemen. I'm Yong'an Lai. I'm from National Taiwan University. In this video, we are going to talk about our research, the phase control tumor stamper. The proposed phase control tumor stamper is a kind of semi-active tumor stamper. The phase of the phase control tumor stamper relative to the structure can be adjusted by applying the fission force at a specific time. Therefore, the phase control tumor stamper can bend to 19 degrees like of structure and have the maximum power flow to reduce the structural vibration. Okay, at first, I will briefly introduce the tumor stamper and the power flow theory. The power flow theory talking about the reason why we want to control the tumor stamper phase. Then I will introduce the mechanism of the proposed phase control tumor stamper, short for PC-TMD. And I will show the phase control strategies and the control algorithm. And finally, is our simulation result and have some conclusions. In Taiwan, the tallest building is the Taipei 101. In this building, one big suspension-type tumor stamper is installed at the top of the building. When the Taipei 101 structure encounters the typhoon or some large wind loads, this giant mass ball will start to sway to reduce the structural vibration. But while the swaying mass ball can reduce the structural vibration, in 1990s, Professor Song proposed the power flow theory to explain how the tumor stamper absorbs the vibration energy of the structure. The theory indicates that the tumor stamper has the best performance when it's just 19 degrees lag of the structure, which has the maximum power flow. If we see a structure implemented with the tumor stamper, when the tumor stamper is just 19 degrees lag of the structure, the interactive force acting on the structure is always done the negative work, and the interactive force acting on the tumor stamper is done the positive work. So it looks like the tumor stamper absorbs the structural vibration energy. The interactive force is like the viscous stamper force when the tumor stamper is just 19 degrees lag of structure. If we see the frequency response function of the structural displacement, the green line, and the phase, in this area, the tumor stamper has the best performance to reduce the structural vibration. The structural response can be reduced from here to here. At the same time, the tumor stamper phase is just close to the 19 degrees lag of the structure. So we think, if we adjust the tumor stamper phase, can the tumor stamper have a better performance? So in order to adjust the tumor stamper phase, we add the fission devices on the traditional tumor stamper. We hope we can adjust the tumor stamper motion by applying the fission force. The fission mechanism is just like the brake mechanism on cars, which can be semi-actively controlled. So this is a kind of semi-active tumor stamper. So how to control the tumor stamper phase? Before control the tumor stamper phase, we may want to know what's the instantaneous phase of the tumor stamper when it's vibrating. However, we found to get the tumor stamper instantaneous phase in real time is a very difficult problem. So in this research, we try not to evaluate the tumor stamper in instantaneous phase. Instead, we use the measurement signals to identify the tumor stamper phase in one of these 4 ranges. For each range, we develop a strategy to control the tumor stamper phase to back to the 19 degrees lag of the structure. If the tumor stamper is just 19 degrees lag of the structure, we can see this. When the structural displacement is 0, the tumor stamper stroke is just at the maximum or minimum. So if the tumor stamper is not just 19 degrees lag of structure, when the structural displacement is 0, the tumor stamper stroke will not just at the peak. So if the tumor stamper motion is shifting like this, which means the tumor stamper phase is in this range, we call this the fast leading situation, because the tumor stamper is running too fast. The tumor stamper reaches the peak value before the structure being 0. In the fast leading situation, because the tumor stamper is running too fast, we can apply the friction force at this specific time. The friction force will hold the tumor stamper motion for a while, like the red line, then release the tumor stamper when the structure is 0. So the tumor stamper can back to the 19 degrees lag of structure. We can use the size of the structure and the tumor stamper state, the displacement and the velocity, to judge this specific time to apply the friction force. So now if the tumor stamper motion is shifting like this, which means the tumor stamper phase is in this range, we call it the fast lagging situation, because now the tumor stamper is running too slow. When the structure is 0, but the tumor stamper not reached the peak yet. In this situation, we still can apply the friction force at this specific time, like this figure. When the structure is 0, we apply the friction force to make the tumor stamper stop as soon as possible. When the tumor stamper is stopped, then release the friction force. The tumor stamper restoring force will take the tumor stamper return to the origin and back to the 19 degrees lag of structure. So the same, we can use the size of the structure and the tumor stamper states to judge the specific time to apply the friction force. If the tumor stamper motion is shifting more than 19 degrees, like this, which means the tumor stamper phase is in this range, we call it the fast overleading situation, because now the tumor stamper is running too fast. And by the way, when the tumor stamper phase is in this range, the tumor stamper absorbed energy may flow back to the structure. There may be increased the structural responses. So in this situation, we can apply the friction force at this specific time, like this figure. We use the friction force to hold the tumor stamper for a long while, and then release the tumor stamper when it's in the right phase. The same, we use the signs to judge when the friction should be on. The last situation, if the tumor stamper force motion is shifting like this, we call it the fast overlagging situation. In this situation, we choose to adjust the tumor stamper phase like this figure, because the sign criteria is the same as the strategy 3. So the sign judgment of each situation is here. Note that the signs of the third and the fourth situation are repeated, so it's only 6 signs trigger the friction force. If we consider the 0 points, because the signs will pass the origin sometime, then 6 judgments will expand to 14 judgments. Why we want to edit the zeros? Because like the fuzzy logic control, if we separate the signals into three parts, not just the positive or negative, then some small disturbance can be neglected, and the control can be more robust. So the phase control procedure is here. We measure the structure and the tumor damper, displacement, and the velocity. Then we get the signs of these signals. Then we use the 14 strategy to check the fusion is on or off. If on, then we apply the normal force to generate the fusion force. If off, then remove the normal force. Okay, the next is show how we model the phase control tumor damper in a structure. We can write the equation of motion of the structure, install a phase control tumor damper. The m subscribe d is the tumor damper mass. The m subscribe s is the structural mass, and u of t is the fusion force. And we can rewrite the equation of motion in the state space form. In state space form, by assuming the fusion force and the external force are piecewise constant in one small time step, then the continuous time state space equation can be derived to the discrete time state space equations. By these equations, if we calculate the fusion force, then the time history analysis can be conducted. So how to calculate the fusion force? If the judgment is off, the fusion force is 0, then the next step can be calculated directly. If the judgment is on, the actual fusion force will be less or equal to the fusion coefficient times the normal force. So the actual fusion force can be calculated by assuming the tumor damper velocity at the next step is 0. Then substituting this condition into discrete time step space equation, we can solve the estimated fusion force. Then the estimated fusion force is judged by the tumor damper is in 6 states or 6 states to get the real fusion force. After we get the real fusion force, then the next step can be calculated. So the time history analysis can be done. The control flow chart is as this figure shows. The phase control tumor damper is a closed loop control by measuring the structure and the tumor damper states and get the signs to judge the fusion by the algorithm table. Then we calculate the fusion force to get the real responses. So all the time history can be done. The following is our simulation result. The first case, we use the Taipei 11 structure to install the phase control tumor damper. The Taipei 11 structure fundamental frequency is 0.14 Hz, about 7 seconds. And in this building, it already has the passive tumor damper. So in this simulation, we both simulate the Taipei 11 structure, install the passive tumor damper and the phase control tumor damper. We first simulate the sinusoidal loss as input to get the frequency response function. If the external force is just match the structural frequency, the traditional tumor damper and the phase control tumor damper both have very good performance to reduce the structural vibration. And the phase, both are very close to the 19 degrees lag of structure. If the external force is a little bit lower than the natural frequency of the structure, the traditional tumor damper lost its performance, and its phase is far than 19 degrees. But if using the phase control tumor damper, the phase can be controlled to close to 19 degrees. So the phase control tumor stamper still have good performance to reduce the structural vibration. The same, if the external force frequency is a little bit higher than the structural frequency, the traditional tumor stamper lost its performance, and its phase is far than the 19 degrees, lack of structure. But if using the phase control tumor stamper, the phase is under control, so it still has good performance to reduce the structural vibration. So by the frequency response function, the phase of the tumor stamper is all much close to the 19 degrees, lack of structure. Moreover, the phase control tumor stamper has both effective frequency range than the traditional tumor stamper. The phase control tumor stamper performs like the multiple tumor stampers, but the tumor stamper stroke is larger. We also simulate the structure under the design wind loads, and no matter in displacement, velocity, or acceleration, the phase control tumor stamper all outperform the traditional tumor stamper. For the traditional tumor stamper, it can reduce 30% vibration in average. If using the phase control tumor stamper, it can reduce about 40% vibration in average. But the only concern is the largest space is required for the phase control tumor stamper. We also discussed the detuning issue. If the frequency of the tumor stamper is not tuned to the structure, the tumor stamper performance will reduce. It's called the detuning issue. In this case, the traditional tumor stamper can endure about 10% frequency ratio detuning in this case. But for the phase control tumor stamper, it can suffer about 30% detuning of the frequency ratio. So the phase control tumor stamper is much robust. And okay, the next we simulate a high-tech factory subject to the earthquake and using the phase control tumor stamper to reduce the vibration. The frequency of the factory is about 1.9 Hz. And we want to reduce the structural acceleration less than 80 Gale under small to middle scale earthquakes. The frequency response is very close to the response under the wind loads. The phase of the phase control tumor stamper is much close to the 19 degrees than the passive tumor stamper, so it outperforms than the traditional tumor stamper. Now we see the response under the earthquakes. From the Fourier spectrum of the earthquake and the response spectrum, we can see this building will resonate under the earthquake. So in this case, the tumor stamper is a good option to reduce the vibration. If using the traditional tumor stamper, the structural acceleration can be reduced from 125 Gale to 70 Gale. If using the phase control tumor stamper, it can further reduce the structural acceleration to only 60 Gale. So the phase control tumor stamper is more efficient than the traditional tumor stamper. And the detuning test also can see the tumor stamper, the phase control tumor stamper can stand larger detuning situation. In this case, the traditional tumor stamper only have 5% frequency tolerance in frequency ratio to remain the 80 Gale target. But for the phase control tumor stamper, it can have about 25% tolerance. So the phase control tumor stamper is much robust. And in this case, we further simulate the sensitivity study of the friction force capacity of the phase control to mass damper. The simulation result shows that if the friction force is not sufficient, the phase control to mass damper performance will reduce. But if the friction is too large, the applied friction force will give the structure an impulse, so the structural acceleration will also not control well. So the friction force exits a suitable range. If the friction force designed well, then the phase control to mass damper has good performance to reduce the structural displacement and the acceleration both. We further simulate another 30 earthquakes to check the feasibility. All earthquake peak ground acceleration are scaled to the 32 scale. And without control, there are 24 earthquakes are not match the requirement in these 30 earthquakes. If we using the traditional to mass damper, there still have 10 earthquakes not match the requirement. If we using the phase control to mass damper, there are only 5 earthquakes not match the requirement. So the phase control to mass damper can reduce the financial risk of the high-tech factory when subject to the earthquakes. Okay, here is our conclusions. According to the power flow theory, the phase control algorithm is proposed for the phase control to mass damper to adjust the phase. So the phase control to mass damper mass moves along the desired chase and back to the 90-degree phase lag to achieve the maximum power flow. And in addition, the power flow back situation can also be prevented. 2. By the phase control, the phase of the phase control to mass damper relative to the structure is much close to the minus 19 degrees. Therefore, the phase control to mass damper has a better performance and effectiveness than the to mass damper, no matter in wind loads or base excitations. And third, the frequency response functions shows that the phase control to mass damper outperforms the traditional to mass damper. Moreover, the phase control to mass damper has both effective excitation frequency range than the traditional to mass damper. The phase control to mass damper performs like the multiple to mass dampers. And 4. From the sensitivity study of the frequency ratio, the phase control to mass damper is robust to stand larger tolerance in frequency ratio inaccuracy. By adjusting the phase control to mass damper tracks the vibration frequency. Therefore, the detuning effect can be mitigated by the phase control. And 5. If the friction force is sufficient, the performance of the phase control to mass damper will drop. However, if the applied friction force is too large, the structural acceleration will be raised by the applied friction force. Therefore, a suitable friction force is required. And thanks for your watching. Goodbye.